This video segment 2C is devoted to recording children's solutions and to a suggested timeline. Why is it important to record children's solutions? Previously, we have emphasized the important role class discussions play in linking children's real or imagined actions with the beads with grouping strategies. Here we explain the importance of recording children's solutions in developing grouping strategies. The link between actions with the beads and grouping strategies arises initially through class discussions as children talk about beads some of the time and about quantity some of the time. As they become increasingly adept at anticipating solution methods, the numerical relationships between the quantities involved become more prominent. Another way to say it is that reasoning about the beads begins to drop out, and reasoning about quantities comes to the fore. And as we have said before, it is this shift to reasoning about quantities that makes it possible for grouping strategies to emerge as part of the conversation. And this is where the use of symbolic notation and number sentences can play an important role. The teacher can use numerical notation to try to write down how somebody is thinking about a problem. In doing so, the teacher links symbolic notation to the child's reasoning and in this sense raises the level of abstraction. Now the grouping strategies are linked to numerical symbols. As the teacher creates written records of several solution methods for the same problem, the class has an opportunity to compare and contrast the solutions, to take note of how they are alike and how they are different. Of course, children can compare and contrast solution methods from listening to the verbal descriptions alone, but verbal comments have no permanence. Written records allow more in-depth discussion. They facilitate communication. The first example we discussed earlier was an addition task. 8 people on the bus, 6 more get on. The first solution for the task that showed 8 people on the upper deck of the bus with 6 more getting on was Andy's solution. She moved 2 beads on the top to the left and 4 beads on the bottom to the left. The final configuration on her rack is shown here as a reminder. The discussion focused on how Andy filled up the 10 on the top rod and then added the other 4 on the bottom rod to get 14. Andy just knew that 10 and 4 make 14. The grouping strategy implicit in Andy's solution is to fill up the 10. To initiate the use of notation, the teacher might say, I'm going to try to write down something that shows how Andy thought about it. Then the teacher can write 8 plus 6 and say, Andy thought of adding the 2 of the 6 to the 8 to fill up the 10, and then adding on the remaining 4 from the 6 to the 10 to get 14. 10 plus 4 equals 14. An alternative way to notate this would be to do the following. We have shown 2 typical ways teachers use numeric notation to show Andy's solution. This type of notation is called pedagogical notation. It isn't conventional notation, but it bears some similarity to conventional notation. We call it pedagogical notation because its primary purpose is an aid in teaching, in pedagogy. It is a way of using numerals and number sentences to record the grouping strategy reasoning that is implicit in the way Andy moved the beads. The same notation works to record the thinking of a child that moved the beads in the same way, but who counted on by ones from 10 to get to 14. The teacher might say, Jacob thought of it the same way, but he counted on from 10 to figure out that 10 plus 4 makes 14. Andy just knew that 10 and 4 makes 14. Since our goal is to advance grouping strategies, the teacher will not write down anything to record counting by ones. The second solution for the task that showed 8 people on the upper deck of the bus with 6 more getting on was Carlos's solution. He moved 6 beads on the bottom to the left. The final configuration on his rack is shown here. The discussion focused on how Carlos figured out 10 by combining 5 from the 8 beads on the top and 5 from the 6 beads on the bottom. Carlos then just knew that 10 and the remaining 4 beads, the white ones, make 14. Again, to initiate the use of notation, the teacher might say, I'm going to try to write down something that shows how Carlos figured it out. And then the teacher can write 8 plus 6 and say, Carlos thought of adding the 5 from the 8 to the 5 from the 6 to get 10. That's all the red beads. Then there's 3 beads from the 8 and 1 left from the 6 to add on. That's 4 more. 10 and 4 equals 14. Here we have shown 2 typical forms of notation teachers use to show Carlos's solution. As she writes the notation, she will go on to elaborate further, gesturing to the beads and to her notation to link the two, and she will get the class involved in the discussion to ensure that they understand the notation and agree that it shows how Carlos figured out the problem. We also note the same notation works to record the thinking of those children that didn't just know that 10 and 4 are 14, but counted on from 10 to get 14. But as we've commented in the previous sample solution, since our goal is to advance grouping strategies, the teacher will not write down anything to record counting by ones. It is important to emphasize that for any solution, notation should always reflect the child's reasoning and not represent a solution method that the teacher has in mind. Now let's turn to a subtraction example. The first solution for the task 13 people on the bus, shown as 10 on the top and 3 on the bottom, and 6 get off, was Darius's solution. Darius moved 3 beads from the left to the right on the bottom, showing that 3 people got off the lower deck of the bus, and moved 3 beads from the left to the right on the top, showing that 3 people got off the upper deck of the bus. The final configuration on Darius's rack is shown here. The discussion focused on how Darius got down to 10, the 10 beads on the top, and then took 3 off of that 10 to get 7. To initiate the use of the notation, the teacher might say, I'm going to write down something that shows how Darius thought about it. Then the teacher can write the number sentences. 13 minus 3 equals 10. 10 minus 3 equals 7, while saying, Darius started with 13. He had 10 on the top and 3 on the bottom. He took away the 3 on the bottom to get down to 10, and then he took away 3 from the 10 and got to 7. That's how he took away the 6. He did it in 2 parts. First, he took away 3 to get down to 10, and then he took away 3 more from that 10. To further emphasize that he took away the 6 in 2 parts, the teacher might circle the 2 3s in the number sentences and say, here's the 6 that he took away. Here's an entirely different way to notate Darius's solution. This version of the notation makes explicit that the initial 13 was shown as 10 and 3. The slash through the 3 indicates that the 3 was taken away, and then we see that another 3 was taken from the 10, leaving 7. We have found both forms of notation productive as a way to show this solution method. Most teachers use these ways of notating interchangeably, using one form at some time and the other form at other times. Nevertheless, it is important to keep in mind that the notation should reflect the child's reasoning and not represent a solution method the teacher has in mind. The second solution for the task 13 people on the bus, shown as 10 on the top and 3 on the bottom, and 6 get off, was Gabriella's solution. Gabriella moved 6 beads on the top rod from left to right, showing that all 6 got off the upper deck of the bus. Here you see the final configuration on Gabriella's rack. The discussion focused on how Gabriella took all 6 off the 10. The form of notation that we have found to be useful for recording this solution method is shown here. After writing the task numerically, 13 minus 6, the teacher shows how 13 was shown as 10 and 3 on the rack, and then shows that Gabriella took all 6 away from the 10, leaving 4. The loop around the 4 and the 3 indicates that the 3 beads remained on the bottom rod and 4 beads remained on the top. So the 4 and the 3 together indicate how many people are left on the bus now. It's 7. Before we leave the discussion of notation, let's take a look at the second form of notation we showed for Darius' solution and see it side by side with the notation we've shown here for Gabriella's solution. We include this image to clarify for the teacher how these 2 forms of notation are alike and how they are different. The rack at the top shows how the task was posed. In each case, the teacher started by writing the task in numerical form, 13 minus 6, and in each case she showed the 13 partitioned into 10 and 3. From that point on, the two forms of notation differ. The one on the left shows that the 3 of the 13 was taken away, and then 3 from the 10. The one on the right shows that all 6 were taken from the 10. In our experience, teachers have found these forms of notation easy to make sense of and use, and consequently so do the students. They provide sufficient detail and yet are not so complex as to be confusing. As a caveat, we caution teachers against showing the 6 as split into 3 and 3 for the notation on the left. Invariably, doing so leaves both the teacher and the students confused. This remark applies to other similar subtraction examples as well. This cautionary note is based on many experiences. We have discussed in detail the two most common solutions to the addition example, 8 on the top, 6 more get on. They are 2 get on the top and 4 on the bottom. All 6 get on the bottom. The first of these solutions gives rise to the filling up the 10 grouping strategy. The second of these gives rise to the combining 5s grouping strategy. Both of these grouping strategies are ones that we know sophisticated children use when reasoning purely numerically. For this reason, we have as an instructional goal that children that would not develop these ways of reasoning spontaneously on their own are given an opportunity to do so, arising from their physical actions with the beads. And the pedagogical notation that we showed is useful for those children to help them advance to eventually reason using these strategies when tasks are posed purely numerically. Now there's a third possible way to move the beads to complete this task. It is to move 1 bead on the top to the left and 5 beads on the bottom to the left. This is the solution method Brian used. Even this way of moving the beads gives rise to a resulting configuration that can be easily read. However, there is no efficient related grouping strategy. Here's what I mean. When reasoning purely numerically to solve the task 8 plus 6, we do not see sophisticated children reason by thinking, I'm going to take 1 from the 6 and add it to the 8 to get 9, and then add on the remaining 5 of the 6 to 9 to get 14. The reason they don't do this is because adding small numbers onto 9 is not easy. The reason the other solutions are common is because each of them involve getting a 10. And 10 plays a special role in our number system. Adding on to 10 results in the related teen number, and by this time, many children in the class know this. For this reason, if a child uses this third way to solve the task, we do not devote time during the discussion to this solution. There is no efficient grouping strategy to relate it to. Of course, a student might report that he solved the task in this way and might even explain how they used the color configurations of the beads to figure out how many are on the bus now. But we do not encourage teachers to spend a lot of time getting others in the class involved in discussing this solution, and we recommend not using numerical notation to record this solution. Doing so inevitably leads to confusion. The solution is not invalid, it simply does not lead to an efficient grouping strategy. In other words, it does not advance the agenda for which this part of the sequence is designed. We have shown several different ways of notating children's reasoning for both the addition and subtraction examples. The principle that undergirds the use of notation is that initially the notation serves as a record of students' reasoning. The notation gradually shifts in function, becoming a means for students' reasoning. This shift in the function of notation is subtle and is not the result of teacher explanation. Rather, it is the result of student reflection. Therefore, the shift takes place gradually and at different times for different students. For this reason, it is important for the teacher to carefully think through notation, as it will be used extensively over many lessons. Where did we get this notation? These ways grew out of situations where we were working in classrooms with teachers as they used the structuring numbers sequence. In some cases, the teacher introduced something spontaneously that proved productive. In those cases, we have suggested that same notation to other teachers who confirmed its value. In other cases, we have worked with teachers to try out various forms of notation that can be thought of as recording the children's reasoning. The forms of notation we have shown here are those that have met the following criteria. First, the notation should be productive for advancing children's development of grouping strategies. Second, the children should agree that the notation shows how they reasoned. It should be a record of their reasoning. Third, the notation should be clarifying and not confusing. That means it should be relatively concise. Not every detail has to be recorded. Fourth, the notation should be relatively easy for the teacher to make sense of and to use comfortably. Finally, we want to emphasize once again that not every solution should be notated. In particular, the teacher should avoid using notation to try to record solutions that are not linked to efficient grouping strategies. When notation is used, it should serve the purpose of aiding communication. It should help children make sense. If children are struggling to make sense of some notation, there's a problem. Notation should make it easier to understand the reasoning, not harder. And it should always reflect the child's reasoning and not represent a solution method the teacher has in mind. It is important that when planning the lesson, teachers anticipate solution methods that children will give and plan which solutions they will record and how they will do so. We also recommend that teachers not notate solutions for the missing add-end and missing subtrahend tasks we described as part of the reasoning without moving the beads activity. In explaining the purpose for recording children's solutions, we have said that numerical notation provides a link between mathematical symbols and the numerical relationships indicated by the grouping strategies that emerged from children's actions with the beads on the arithmetic rack. In particular, we are interested in the strategies for addition and subtraction tasks that involve numbers to 20 with an emphasis on teen numbers. The tasks in Part 2 of the structuring numbers sequence are precisely the types of tasks involved in developing these number relationships. For this reason, we recommend that throughout this portion of the sequence, beginning with reasoning by moving the beads and continuing throughout, teachers use the types of notation we have shown to record children's solutions. Even so, as we have noted when presenting the examples, we suggest that teachers use tasks for several days before introducing notation. The reason for this suggestion is that it is helpful for students to focus for several days entirely on thinking through the numerical relationships, that is, the grouping strategies that are implicit in the way the beads are moved. After 2 or 3 days, when that is the entire focus, it is appropriate for the teacher to begin using notation. By that time, a number of students in the class will be starting to think and reason numerically. The repeated and persistent use of notation is crucial to children's developing meaning for numerical symbols. In this way, rather than being introduced in a top-down fashion, numerical symbols come in as a means to express reasoning the children have already engaged in. The symbols are a record of their already completed reasoning activity. Later, when children encounter numerical symbolism on its own, they have a basis for making sense of it. I want to make one additional remark about notation here. The activities in this part of the sequence involve both addition and subtraction tasks that are intermingled throughout the lessons. That is, teachers do not use only addition tasks and then later introduce subtraction tasks. Rather, they are used in conjunction with each other, as we have illustrated in some of the suggested task sequences. Even so, teachers we have worked with have found that it takes them some time to become proficient with using the suggested notation, and for that reason, teachers typically introduce notation for addition tasks several days before they introduce notation for the subtraction tasks. Doing so not only gives teachers an opportunity to become comfortable with one format of notation before using another, but also gives students an opportunity to do so as well. This rationale is simply pragmatic. In this video group, we have given detailed information about the second part of the Structuring Numbers instructional sequence. Here we show a timeline for the entire sequence that shows where Part 2 fits in. Typically, teachers devote about 3.5 weeks to Part 1 of the sequence before moving to Part 2. As an aside, we notice that it is not necessary to continue with activities from Part 1 while also beginning Part 2, because reading the rack is an integral part of each of the activities within Part 2. Children that may not yet be completely proficient with reading the rack efficiently continue to have opportunities to do so as they engage in the activities within Part 2. The timeline shows that Part 2 continues almost to the end of the entire sequence. The detailed timeline we show for Part 2 indicates that the reasoning by moving the beads activity is used for about 2.5 weeks before it gives way to the reasoning without moving the beads activity, which is itself used for about 2.5 weeks. The anticipation activity serves as a transition between these two activities. It is first used after several lessons of reasoning by moving the beads, and it then is combined with that activity to comprise a lesson. When the shift is made to reasoning without moving the beads, the anticipation activity is still used as part of the lesson for some time. This overlap is deliberate. When students begin to reason by moving the beads, some of them very quickly begin to think about which beads they would move even before they do so. The anticipation activity capitalizes on this advance by posing tasks where students begin by moving beads on their rack, but then are asked to try to complete the action and figure out the total mentally without completing the action with the beads. In this way, the anticipation activity provides important conceptual challenges for these students that help them to advance their learning. And at the same time, those students that are not yet able to complete the task mentally have access to their racks so that they can complete the task by moving the beads, or at least by touching the beads on the racks. In this way, the teacher ensures that every student participates in every instructional task posed and is able to do so in a personally meaningful way. Imagination Bingo comes in toward the end of Part 2 and is an activity that provides variety in format and also contributes to solidifying children's conceptual understanding of the relevant number relationships for numbers to 20. Part 2 forms the heart of the Structuring Numbers sequence. We encourage teachers to use their judgment about the total amount of time to devote to this part. At the same time, we remind teachers to keep moving forward. These instructional activities are designed so that children continue to make conceptual advances even as they move to more conceptually challenging activities. The next video describes Part 3 of the Structuring Numbers sequence in detail. We note that there is a fourth video group that talks about the teacher's role in successfully implementing the sequence. It is devoted to two main issues. One relates to planning lessons, including selecting which activities to combine to comprise a lesson, and for any specific activity, selecting which tasks to pose to enhance the learning opportunities for students. The second issue is how to orchestrate productive class discussions. Examples are used to illustrate both of these issues. This fourth video group can be viewed meaningfully at any time. It is not necessary to first view all of the videos that describe the details of the instructional activities.